Welcome to part 3 of our lecture video series for Friday, April 28th, where we now are going to discuss our second method for theoretically determining the heat of a reaction, and that is by using what's called Hess's Law. Now, before we get into the definition of Hess's Law, what I want to do is I want to kind of build a case for you as to why Hess's Law is something that we care about. So let's think about kind of the means that we have so far of determining the heat of reaction. The first was from directly observed empirical data, specifically temperature change data. So that was when we used calorimetry to look at heat exchange. And the second was by using our standard enthalpies of formation. So we were looking at reactions that occurred at standard conditions and looking at the difference in the amounts of mole quantities and their heats of formations of products against those of the reactants. So then why is it that I am now introducing to you this now second way of getting a theoretical determination of a heat of reaction? So let me ask you this. What if we're trying to determine the heat of a reaction for some reaction that is unobservable, meaning there's no way for us to be able to collect any temperature change data, we can't do calorimetry on it, it's not a reaction that we can easily isolate in the lab. And on top of being a reaction that's unobservable, it's also a reaction that doesn't occur at standard conditions, meaning we're now unable to use our standard heat of formation method for determining the heat of reaction. What is left? Now, if you think that these kinds of reactions are rare, you might be surprised. There's an entire field of chemistry called atmospheric chemistry, which is kind of a crossover between analytical chemistry, physical chemistry, and environmental chemistry, where scientists are very concerned, as you can imagine, in the era of climate change, what kinds of chemical reactions are happening in various layers of our atmosphere, and in what way they're happening, and in what way they are releasing or absorbing heat. So you can imagine if you are a scientist who's trying to determine the heat of some atmospheric reaction, one, you're not going to be able to send equipment up to the lab to get some kind of like isolated environmental system that can have like calorimetry performed on it. And two, even if you were able to do that, you would be doing that up at really high altitudes, right? Way up high in the atmosphere. And we are certainly not at standard temperature and pressure under those actual real world conditions. So Hess's law becomes really important for reactions that are either completely theoretical, meaning they have not been observed ever, they're only theorized to have happened, or reactions that we simply don't have the means of observing physically because of the limitations of our instrumentation. This is where Hess's law comes in. So let's define Hess's law. Now, all that Hess's law really is like the manifestation of enthalpy being a state function. So Hess's law states that since enthalpy is a state function, meaning we only care about initial and final states and not how we got from our initial state to our final state. So since enthalpy is a state function, we can quote unquote build reactions from other reactions whose heats of reaction are known. Meaning we can kind of build a bear, in a sense, a reaction of interest to figure out its heat of reaction by looking at various combinations and manipulations of reactions that we do know. So we can combine manipulations of some known reactions, and more specifically, their heats of reactions, to create both our reaction of interest and find its heat of reaction. So there are two main kind of rules that comes with Hess's law. So the first is that if a reaction is going to be reversed to build the reaction of interest, then the sign of its heat of reaction is then flipped. So if it was once a positive heat of reaction, the inverse or reverse of that will be the negative. And if a reaction is scaled, meaning multiplied or divided by some number, then the heat of reaction is also scaled or multiplied or divided by that number. And the idea here is that the sum of the heats of reactions that are kind of like our building blocks or our component reactions should ultimately wind up giving us our actual heat of reaction of interest. So let's look at a really generic example where instead of looking at actual chemistry, we're just going to look at some letters as placeholders. So let's take a peek at this. What is the heat of reaction for the reaction where A comes together with 2 moles of D to create 3 moles of B? So this is the reaction that we care about. It is also the reaction that we are trying to build, and it's also the reaction that we want its heat of reaction. So let's see if given these reactions, let's call them reaction 1, 2, and 3 in order, let's see if we can't use these given reactions to try to, in some way, build the reaction of interest. So let's get started. Let's just jump right in. Let's see here. So our reaction, I'm just going to break this down into steps. So the reaction of interest requires 1 mole of A on the reactant side. So if I'm looking through the kind of toolbox, the Lego kit that I have in order to make this reaction, I'm going to look for a reaction that contains A, and I see that reaction 1 contains A. However, I notice that it has 3 moles of A instead of 1 mole of A, and it's on the product side. So if I want to get 1 mole of A, compared to the 3 moles of A, I'm going to need to divide reaction 1 by 3. And since I've also now have this opposite side placement of where A is, I'm going to need to flip reaction 1. So not only am I going to have to take reaction 1 and reverse it, but I'm also going to need to divide everything by 3. Now, what does that mean is going to happen to my heat of reaction? So if I have the heat of reaction for reaction 1, if it is going to be flipped, the sign is going to change. And if it's going to be divided by 3, I'm going to multiply it by 1/3. So this is kind of the result of what needs to happen if we're going to build our reaction. So let's take reaction 1 and flip it and divide by 3. So flipping it gives us 3A going to 2C, and then dividing by 3, this becomes A going to 2/3 C. So A going to 2/3 C, this now has a heat of reaction that is negative 1/3 the heat of reaction it originally was. All right. So good, I've taken care of my reactant A. How about now my reactant D? So our reaction of interest requires 2 moles of D on the reactant side. So I'm going to go looking through my reactions that I have to build my reaction of interest, and I notice that both reaction 2 and reaction 3 have D involved somehow. Okay. Since they both involve D, I think I'm going to switch tactics here. So our reaction of interest has no C involved. Meaning that I'm going to need to manipulate some of my other reactions. Oh gosh. So my other reactions such that my 2/3 C cancels out. So I need a reaction that has 2/3 C on the reactant side. This will cancel out with my manipulated first reaction. So if I'm looking at my reactions that are given, I see that, okay, well, reaction 3 involves C. And specifically, it has 2 moles of C on the product side. So my reaction of interest has no C involved, meaning I need a reaction that has C on the reactant side. However, reaction 3 contains C on the product side, so I'm going to need to flip reaction 3. And then I'm also going to need to fix my mole quantity of reaction 3 because I have 2/3 moles C, and I need to cancel this out. So I need to divide my 2 moles of C by 3 so I get 2/3. So divide reaction 3 by 3. So let's do that. So let's first reverse reaction 3. That is 3D plus 2C going to 3B. Okay, that'll give us the flipped heat of reaction for reaction 3. And now I need to divide every coefficient by 3, so this becomes 1D and 2/3 C going to 1B. So this is now negative 1/3 the heat of reaction of 3. Okay. So far I have this available to try to build my reaction because I've got A, and I have now gotten rid of my C's, which is good because C is not involved here. Okay, so far I've got A going to B when it reacts with 1D. Okay, well, let's look at our reaction of interest. We need 2 moles of D on the reactant side. So the reaction of interest needs 2 moles of D on the reactant side, and we currently have 1. So let's put all of our D on the reactant side. So let's go ahead and flip reaction 2. So since reaction 2 contains D, specifically we have in reaction 2 1 mole of D on the product side. Since we need D on the reactant side and reaction 2 has D on the product side, we're going to need to flip reaction 2. So let's see what happens when we do that. So reaction 2 was 2B going to D. So that means that this is going to become now B going to D going to 2B. And the heat of reaction for reaction 2 is going to be flipped in sign. Okay, let's see if what we have so far will give us what we want. So we have flipped reaction 2's heat of reaction. We have flipped and cut in third reaction 3. And we have also flipped and cut in third reaction 1. So I'm just going to rewrite all these things, including the C's that have canceled. So let's see if we can make our reaction of interest based on what we've got going on so far. So we have A going to 2/3 C and this is going to be the negative heat of reaction 1 cut into thirds, so negative 1/3. Okay, we also have reaction 3 that was manipulated, so we have D going to, nope, D plus 2/3 C going to B. We also had to flip and reverse this reaction. And then lastly, we had D going to 2B. This was simply a reversal, so the sign of the heat of reaction for reaction 2 is going to change. We know that our 2/3 C's will cancel because we did that by design. Let's see if we sum to get the reaction that we care about. So we have A coming together with 1, 2, 2D's in order to form 1, 2, 3, 3B's. Is that the reaction of interest? Yes it is. So we have the reaction of interest. Yay, we were able to build our Frankenstein's monster. But then how do I find the heat of reaction? Well, since I added up these reactions to get the reaction of interest, then I need to now add up all of their manipulated heats of reactions. So that's going to be negative 1/3 times the heat of reaction 1 plus negative 1/3 of the heat of reaction 3 plus the negative of the heat of reaction 2. So because I followed all my manipulations through into the enthalpies of each of these reactions, when I sum these together, I should get the heat of reaction for the reaction that I care about. All right. I think what we're going to do is we're going to go ahead and save this example. For a warm-up on Monday, May 1st. And then from there, we will move on to our next topic, which is gases and gas laws. So thanks, y'all. This was it for thermochemistry for Chem 210, and I hope you have a lovely weekend. Thank you.